Hi, in this session we shall deal with the fundamental theorem of arithmetic. This session is for grade 10 on real numbers. Before we go to the fundamental theorem of arithmetic, let's revise what a prime number is and what are the composite numbers. A prime number is a natural number meaning the counting numbers like 1, 2, 3 like that. And we can say a prime number is a natural number greater than 1 that cannot be formed by multiplying two other natural numbers. In other words, we can say that a prime number is a natural number which is divisible by two natural numbers, and those two natural numbers are 1 and the number itself. So the point to note here is that it is divisible by only two and exactly two numbers, and those two numbers are number 1 and the number itself. And what are the composite numbers? A composite number is a natural number which is greater than 1 and which is not a prime number. Then that number is called as a composite number. So we have seen a prime number, and the number which is not a prime number is a composite number. And what about the number 1? We know by these definitions, because you see the prime number is greater than 1 and a natural number greater than 1 can be a composite number. We notice that 1 is neither a prime number nor a composite number. Okay, so now let's talk about the fundamental theorem of arithmetic. The basic idea of this fundamental theorem of arithmetic is that any integer above 1, meaning greater than 1, is either a prime number or it can be made by multiplying the prime numbers together in a unique manner. So the unique manner will be there if we ignore the order. So let's say 2 multiplied by 3, and it can be 3 multiplied by 2 as well. So we shall have to ignore the ordering of them. Let's take some examples. Let's say we have numbers 2, 3, 4, 5, 6 like that. We have here up to 14, and then there could be many more, and let's say there is an in between number 32,760 and so on. So number 2 is a prime number, number 3 is a prime number, number 4 is a composite number, number 5 is again prime, 6 is composite, 7 prime, 8, 9, 10 are composites like that. So let's see if we consider let's say a composite number 4, and from the basic idea here we notice that the composite number can be formed by multiplying the prime numbers. So number 4 is formed by the multiplication of number 2, which is a prime number. So 4 is equal to 2 raised to power 2. Similarly, let's take another let's say composite number 2, which is composite number 10, which is formed by multiplication of 2 and 5. So again 2 and 5 are the prime numbers, and a composite number is formed by multiplication of two prime numbers. In fact, as this basic idea says, that every composite number can be written as a product of powers of prime numbers. So it could be, let's say another example could be the 12, which can be written in the form of powers of 2 raised to power 2 multiplied by 3. So the basic idea is saying that any composite number can be formed by multiplication of prime numbers, and the prime numbers, they will be unique to obtain that given composite number. So now let's move on to our fundamental theorem of arithmetic. This is the theorem 1.2 in the textbook, and it states that every composite number can be expressed, that is factorized, as a product of prime numbers, and this factorization is unique apart from the order in which the prime factors are arranged or they occur. So basically it can be stated in the other words as well. So we can say that the theorem states that any composite number, meaning any number from let's say you can think of, and it is if it is a composite number, it can be factorized as a product of prime numbers in a unique way. And unique way will be by ignoring the order in which the primes occur. So let's take example of number 12. This can be decomposed into 2 multiplied by 2 multiplied by 3, which is 2 raised to power 2 multiplied by 3. So this 2 raised to power 2 multiplied by 3 is unique. So the prime factors are 2 and 3. You cannot have any other manner in which you can obtain number 12 by having prime numbers on this side. You cannot obtain it. There is only one unique way that you can obtain number 2. So let's see it in some other words again. So this theorem can be expressed in some other words by saying that any composite number, for any given composite number, there is one and only one way to write this composite number as a product of prime numbers. So as long as we are not particular about the order in which the prime numbers are arranged. So what it states is that by ignoring the ordering of the prime numbers, we can obtain any composite number in a unique manner by unique prime factors. Let's talk about the same theorem in some more different words here. So the other way to state is that the prime factorization of a natural number is unique except for the order of its factors. So let's take example of 32,760. It can be expressed as 2 multiplied by 2 multiplied by 2 multiplied by 3 times 3 times 5 times 7 times 13, which is equal to 2 raised to power 3 into 3 raised to power 2 into 5 into 7 into 13. And if you see here, 2 is a prime number, 3 is a prime number, 5, 7 and 13 are prime numbers. So we have expressed 32,760 into its prime factors on this side, and this way is always unique. So what it is saying is that this is the only way to factorize 32,760 using prime numbers. There is one more point that we should remember when we talk about the fundamental theorem of arithmetic. So let's say in general, for a composite number C, we factorize it as C is equal to P times P1 into P2 into P3 into P4 and up to Pn. So a composite number C is P1 times P2 times P3 times P4 up to Pn, where the P1, 2, 3 and Pn are the prime numbers which are written in the increasing order. This increasing order or the ascending order is important, and it can be expressed mathematically as P1 is less than or equal to P2 is less than or equal to P3 is less than or equal to P4 and all the way up to Pn. So this increasing or the ascending order is important. So if we agree on arranging all the prime factors in increasing or let's say ascending order, then the prime factorization that we shall obtain for any number will be unique. So let's take example again of 32,760. So if this is expressed in its prime factors and the prime factors are increased in increasing order, either equal to or less than this format, P1 is less than or equal to P2 and P2 is less than or equal to P3, just like see here, all the 2's are first, then there are 3 and 5, 7 and 13. So this manner or this factorization will be unique, and that is what the theorem, the fundamental theorem of arithmetic states.